So I'd like to give you an idea about what your computer is thinking when you type a number into your computer. So let's do this number. And when we humans look at that number, we say something totally different than just saying the digits 3, 0, and 2. We actually call this 302. And the reason, even though there's no hundreds written on here, we just know because of the placement of that 3 what it's supposed to be. The reason that is because we work with a base 10 system. And base 10, you might remember from when you were younger learning about this placement. But base 10 means that we have 10 digits. Those digits are 0 all the way through 9. There's 10 of them. So we have a base 10, we have 10 digits that are available to us. In addition to having 10 digits available to us, each of these spots, starting at the right side, goes up by a power of 10. So that's why we call this the 1 spot, because 10 to the 0 is 1. We call this the tens spot, because 10 to the 1 is 10. And we call this the hundreds spot, because each time we move to the left, we go up by a power of 10. Well, you'll never guess what a binary system uses as its base. If we humans have 10 digits, and we use base 10, so when I'm looking at this number 302, the reason I'm saying 302 is because I'm using this digit, which is a 3, and I'm multiplying it by that placement, which is 100. Plus, I'm taking this digit of 0, and I'm multiplying it by that placement, which is the 10. And then the last digit is a 2, so I'm going to add on 2 times that placement, which is just the 1. So that's how I get that 3 times 100 is 300, nothing, plus 2 is 302. So that might seem ridiculous. You're like, we learned this way long time ago, but when we talk about a binary system, it works exactly the same way, except for we don't have 10 digits anymore. Guess how many digits we have with a binary system? If you guess 2, you're right. There's 0 and 1, and that's it. Those are the only digits we have to work with. So we can have as many places as we want. I'll do 3 spots. But now, instead of going up by a power of 10, like we did with a base 10, we're going to go up by a power of 2. And you can keep going as long as you want. We'll just talk about a 3-digit number for now. So we're going to go up by powers of 2. So instead of this being the hundreds spot like it was in our decimal number system, it's going to be the 4s spot. And instead of this being the 10 spot, it's the 2s spot. Anything to the 0 power is 1, so that's still going to be the 1 spot. But now another difference is the only digits I can use here are a 1 or a 0. So we need to talk about, let's place those, here I'll put a 1, a 0, and a 1. This is not the number 101 because we're not in decimal anymore. We are now in binary. But I'm going to still do the same exact process. I'm going to take this 1 and multiply it by the spot it's in, which is the 4s. Plus, I'm going to take this 0 and multiply it by the spot it's in, which is the 2s. And I'm going to take this 1 and multiply it by the spot it's in, which is the 1s. So altogether, I have 4 plus 0 plus 1, which in our number system is a decimal number 5. we call base 10 decimal. So 101 in a base 2 language is the same as a 5 in a base 10 language. And that's how you can convert from a binary number to a decimal number. Let's practice by trying a couple of these. I would strongly suggest when I write this problem on the board to maybe hit the pause button and try it on your own first to see what happens, and then we'll work through it together. So let's try this number, 0101. What is this number if we wanted to know what it was in base 10 or decimal? So right now it's written in base 2, it's written in binary, and let's do a conversion. So again, I always start at the right, and I know I have to go up by powers of 2. And I like to write them all out. So I'm going to take this first digit times 8 plus the second digit is a 1 times 4, the third digit 0 times 2, and the last digit 1. And if I add those up, that is a 5. But what if I put something else on there? What if I made this an 8-bit number? 1, 2, 3, 4, 5, 6, 7, 8. Now there's 8 bits. 8 bits, by the way, is what we computer programmers call a byte. So this is a full byte of information. So again, we would start at the right and just go up. Now this 2 to the 7th, notice that doesn't really matter because it's going to be 0 times it. So one little trick that I like to use is I just get rid of all those zeros because 0 times anything is 0. So that's just too much work. So 2 to the 6th power is 64. 2 to the 4th power is 16. 2 to the 2nd power is 4. And 2 to the 0 power is 1. And if I add that all up, I personally would take 16 plus 4 first, and then I would take 64 plus 1. I see that that's a decimal number 85, which is all fine and dandy if binary numbers only work for numbers, for integer numbers at that. But I bet that there is a letter that is associated with 01010101. So it's got a decimal number 85. But if you look at the chart that we looked at before, the ASCII chart, you'll notice that it also has a letter associated with it. So look for the 01010101, or you can look for the number, the decimal number 85, and you'll see that that is associated with a capital U character. So there's the same exact binary byte with 2 very different meanings.